In this video, we will be looking at how to use calculus and derivatives to help us solve optimization problems. And in this video, we will be specifically looking at word problems related to numbers and shapes. So first thing, just very general for optimization problems and how to be successful with them. Number one, make sure you read the problem carefully. If you can draw a diagram, make sure you do that. For example, if a shape is involved, it would be very helpful to have that visual. And then start writing some let statements to introduce any variables. Now, once you have your diagram and you've read carefully, you need to look at your word problem and see what quantity are they asking you to maximize or minimize, because whatever that is, that's what your equation will have to be about. So if I wanted to maximize the volume of a certain shape, I'm going to need an equation to represent that volume because I want to find the optimal value for that function. And how do we find the optimal value? Well, we're looking for the max and min within a domain. So we want to find the critical values by finding the derivative and setting it equal to 0. And then to see which values are maximum or minimums, we're going to try some test values. We're going to test the critical points and we're going to test the endpoints of our domain. And then we can write a therefore statement to actually answer our question, making sure we have appropriate units, appropriate rounding, or keeping our answers exact, depending on the question. So we're going to look at 3 different examples in this video. Some of them are going to be identical to grade 10. However, we will be using calculus to solve for these optimal values. So in our first example, you have a piece of cardboard that is 40 centimeters by 20 centimeters. When an identical square is cut from each corner, the cardboard can be folded into a box with no lid. What size cut should be made to maximize the volume of the box? Round to the nearest tenth. I definitely need a diagram here. So I have a piece of cardboard. (40 centimeters by 20 centimeters. And there are cuts that are going to be made in each corner. And when I make these cuts, I'm gonna fold on the dotted line so that in the middle, that's gonna be the base of my box. And then these pieces are going to be gone. So each of the remaining rectangles are going to be the sides of this box. Now this box will not have a lid on it. Okay, again, rereading what the question asks me, I need to find the size of the cut to maximize the volume. So I'm gonna need to create a volume equation, but I also need to introduce some variables. So I'm gonna say let x represent size of cut. And in my diagram, this, all of these segments here represent the cut, so they're all x. Now, if I want to maximize the volume, what do I already know about the volume of a rectangular prism? I know it's length times width times height. Well, if you look at the diagram where these cuts are made, this here is the height of my box. So my box will have a height of x. And then there's my length, there's my width. Now the original length of this cardboard box was 40 centimeters. But then I removed x from one side and x from the other. So that leaves us with 40 minus 2x. And there's the length. Likewise, the width was 20 centimeters, but I'm removing an x from the top and bottom. So 20 minus 2x is the width. So now I have length, width, and height, and it's all about x, so I can write a nice equation for the volume. So V at x equals, it doesn't matter which way I multiply these side lengths, so I'm just going to write them like this. Now that I have the equation that I need to maximize, I know I'm going to have to find the derivative to find those critical values. But I also have to consider not just the critical values, but the endpoints. So going back here to x, what is x allowed to be? Well, it has to be greater than 0 and not equal to 0. Otherwise, I can't actually create the box if no cuts are made. And then I have to think, well, what's the maximum I can cut off? So I'm going to look at my shortest dimension, which is 20 right here. If I cut from both sides 10 centimeters, then I have nothing left because that'll fulfill the full 20 centimeters. So the maximum the cut can be is just under 10. So that's going to be my domain that I'm going to use later on. Okay, now let's get into that derivative. Now I can take my derivative from this factored form, or I can expand and simplify and use my basic power rule. I'm going to expand and simplify because this is going to be very quick to expand and simplify. So we have 800 minus 80x minus 40x, so that's minus 120x plus 4x squared, and then distribute that x in. And while I distribute the x in, I'm just going to rearrange. So I'm going to put 4x cubed first, then 120x squared, then 800x. And now I'm ready for my derivative. So 12x squared minus 240x plus 800. And now that we have the derivative, let's set it equal to 0 and solve for those critical points. Now I can factor out a 4 from here, but unfortunately, even if I do that, I'm not going to be able to factor this expression, so I'm just going to go to my quadratic formula. So I'll have x equals 60 plus or minus the square root of 1200 over 6. And it said round to the nearest tenth, so I will go ahead and do that. So I'm going to do 60 plus the square root of 1200 divided by 6. I get approximately 15.8. If I do 60 minus, I get approximately 4.2. Now, looking towards that domain that we wrote, x has to be between 0 and 10, so this value is out of domain. So I'm not even going to consider it. And now I'm going to start testing some values. So what am I going to test? I'm for sure going to test my 4.2 from the critical point. Now, there's no purpose of me testing 0 and 10 because that'll give me a volume of 0, but I'm just going to test really close to it. So I'll test 0.1, I'll test 9.9. So when I plug in my 4.2 and when I plug it into my calculator, I will use this exact value instead of the rounded one, just to maintain some accuracy. When I sub in 4.2, I get approximately 1,539.6. If I sub in 0.1, I get 78.804, definitely not a maximum. And when I sub in 9.9, I get 625.716. So our maximum is definitely at the critical point. So now we know that the cut should be a 4.2 centimeter by 4.2 centimeter square. So let's write our therefore statement. Therefore, a 4.2 centimeter by 4.2 centimeter square cut will maximize the volume. All right, so to recap, I had a piece of cardboard, I was making these X by X centimeter cuts so that I could create this rectangular box with no lid. I had to maximize the volume, so I had to create a volume equation. My height was X, my length and width came from the original cardboard length and width where 2 X's were removed. So here we are. Once we found that volume, it wasn't about the word problem anymore. We found the derivative, we set it equal to 0 to solve for those critical points, and we tested that critical point. But of course, we had to think about what X could be realistically. It had to be greater than 0, and it had to be less than 10 if I wanted a box to be cut. Any more than 10, I couldn't take 10 from 20 centimeter 2 times to actually create a box. And anything more than that, not possible. So that's where those numbers came from. So I tested values close to the endpoints as well, and we found that the critical point was the maximum. And then we could write our therefore statement. All right, let's try a number example. And this one actually does come straight from grade 10. In grade 10, we did this differently, but now we'll have a more efficient maybe way to do this. So 2 positive integers have a sum of 8. Determine the 2 numbers if the sum of their squares is a minimum. Okay, no diagram here, but I know I have 2 numbers. Okay, so I'll just say let X represent first number, let Y represent second number. I'm told the sum of the 2 numbers is 8, so X plus Y equals 8. This is definitely not what I'm trying to maximize or minimize. This is just going to be a helper equation. So I'm just going to isolate for one of my variables. And I'm going to put it to the side. Then it says to find the 2 numbers if the sum of their squares is a minimum. That's what we're trying to optimize here, the sum of the squares. So what does sum of the squares mean? So I'm just going to say S for sum of the squares. So here are my 2 numbers. I have to add, so sum, add their squares. So here it is, X squared plus Y squared. But this, I can't take the derivative. I have too many variables here. But thankfully, we have this. We know that Y is equal to 8 minus X. So I'm going to go in and replace Y with 8 minus X. So now we have S equals X squared plus 8 minus X squared. Now I'm ready. So I can find the derivative from this, or I can expand and simplify and then find the derivative. In this example, you know what? I'm not going to clean up. I'm just going to go straight to my derivative. So the derivative of X squared is 2X, and then I have a chain rule. So 2 times the inside to the power of 1 times the derivative of the inside, which is just -1. And now I'm going to clean this derivative while also setting it equal to 0. So we have 2x, and then here 2 times -1 is -2. So I'm distributing -2 into 8 minus x. So -2 times 8, -2 times -x. Okay, so now I'll bring the -16 over. I have 4 x's. 4 equals x. That's my critical point. So I know I'm going to use that in my test. Now, something I didn't do at the very beginning is write the restriction for my variable. And since my sum of the squares equation was all about x, I need to restrict x. So from the very beginning, we know that we need 2 positive integers. So I can say for my restriction here that x is an element of integers. And what does x have to be? Well, if my 2 numbers have to add up to 8 and they have to be positive integers, then the first number that x is allowed to be is 1. And the largest number it's allowed to be would be 7. So that's going to give me my test values. So I'm going to be testing the sum when x is equal to 1, when x is equal to 7, and when x is equal to 4 for that critical point. And I am going to be plugging in to this sum of the squares equation, not the derivative. So when I plug in x equals 1, so I would have 1 squared plus 8 minus 1 squared, my sum is 50. When I plug in 7, my sum of the squares is also 50. And when I plug in 4, I get 32, and this is the minimum. So that means x, my first number, is 4, and my second number would be 8 minus 4, which is 4. So these two numbers will minimize the sum of the squares. So now I can write my therefore statement. Therefore, the two numbers 4 and 4 will minimize the sum of the squares. Final example, also coming from grade 10, but now we have our calculus twist. A lifeguard has 200 meters of rope and some buoys with which she intends to enclose a rectangular area at a lake for swimming. The beach will form one side of the rectangle, with the rope forming the other three sides. Find the dimensions that will produce the maximum enclosed area. Okay, starting off with a diagram. So we have the beach, let's say here, and we have rope like this, and we need to maximize this area. So what do I need? I need a length and a width. So I'm just gonna say let x represent the length, let y represent the width, and I'll label that in my diagram. X, y, y. All right, we want to maximize the area. Well, area is x times y, length times width, but I can't take the derivative of that. Too many variables. But I do have another piece of information that's important, and it's the 200 meters. That 200 meters of rope has to cover this y, this x, and this other y. So that is x plus 2 y's should be 200. And now I can isolate for one of my variables. I'm just going to isolate for x. Bring the 2y over, and now I can go ahead and replace x with y, or with this expression. And then my whole equation is going to be about y. So I'll have y times that x. And now I'm just going to expand and simplify this, and then I'll take the derivative. Here in grade 10, you would have found the zeros and averaged them. But we'll do our derivative, and we'll have 200 minus 4y, which we can set equal to 0 and solve. So we can bring that 4y over and divide by 4, and we get 50. So now, what are we going to test? Well, I'm going to test the area when the width is 50. But what about my other restrictions? What else can y be? Well, y can be starting from 0, because we can't have a negative width. And what's the maximum the width can be? Well, I have two widths here, and I have 200 meters of rope in total. So if this was as close to 0 as possible, we'd have 100 meters available for the two widths each. So here we are. So that's me just using logic and looking at my diagram. I can also look at this equation here and say, well, obviously the length has to be positive. So what value here will get me the smallest positive number? Because anything beyond it will take me into the negatives. So if you imagine setting x equal to 0 and solving for y, bring the negative 2y over, divide out the 2, you get 100. If I go beyond 100, like 101, I'm going to have a negative length. That's not okay. So now, going back to my testing, I'm going to try 50, I'll try 0.1, and I'll try 99.9. When I plug in that critical point of 50 for my area, so I'm going right in here, or here, doesn't matter, I get 5,000. meters squared for that area. When I plug in 0.1, I get 19.98. That's not good. When I plug in 99.9, I also get 19.98. That's not good either. I want my maximum. Here it is. So here's the width. To get my length, I'll plug it in here. 200 minus 2 times 50, and I get 100 meters. So now we can write our therefore statement. Therefore, a 50 meter by 100 meter rectangle will maximize the swimming area. And there we are. So in all of these examples, we read the questions carefully, drew a diagram if it was related to a shape, wrote out an equation about what we need to maximize or minimize. And sometimes we would have that little side equation to help us make our optimal equation about one variable. And once we did that, it was back to basics. Find the derivative, set it equal to 0 to get your critical points, and then do your test values. And there we are.